Space telescope is, in a way, a little like Galileo's first telescope. Wherever Galileo pointed his telescope, he made major new discoveries. Look at the moon, you find mountains and craters. Look at Saturn, you find rings. Look at the Milky Way, and you find it is littered and composed of stars.
If you could look back in time, when would you look back to? Early man? The time of the dinosaurs? Or the birth of our planet?
We like to say telescopes are like time machines, and of course the reason that this is possible is because light takes time to travel. So the street lamp across the street takes a teeny tiny fraction of a second for the light to reach your eye. The light from the sun takes about 8 minutes to reach the Earth. So in essence, we're seeing the sun as it was 8 minutes ago.
Now, a new telescope that's more powerful than anything that's ever been sent into space is looking at some of the farthest and oldest objects yet. It's called the James Webb Space Telescope, or JWST, and it can see back to the beginning of the universe, when the first galaxies started to form and emit light after the Big Bang.
One of the great things about telescopes like this is they're really designed to see the entire universe. So all the way to 13.5 billion years into the past, all the way to our cosmic backyard of the solar system, and everything in space and time in between.
Finally, after 30 years in the making, a successful launch into space, 50 successful deployments, 1 million miles traveled from Earth, months of cooling to near absolute zero and calibration. It has delivered its first full-color science-quality images. These images showcase the telescope's powerful instruments and offer a preview of the science projects to come.
These first images really do signify the start of science operations. We have over a year of observations already planned, some really exciting things that we already have designed to do in the first year of operations.
The hope of scientists is to uncover the greatest mysteries of the universe today.
We would like to observe galaxies as far away as possible.
Red giant stars in the disk of Andromeda.
Star-forming regions. One is in the Milky Way, our galaxy, and two nearby galaxies, the Magellanic Clouds.
The TRAPPIST-1 system, what we can call the rock star of exoplanet.
TNOs, these are objects that are orbiting beyond the orbit of Neptune, so in the coldest regions of our solar system.
How stars, galaxies, planets, etc. formed, and that really helps us understand how we fit in.
So we have all these very specific, questions that we've planned to try to answer, and I think we'll for sure answer those. But I think we'll also learn things that we haven't even dreamed of yet.
Liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
In 1990, the Hubble Space Telescope successfully launched aboard the Space Shuttle Discovery. It's been serviced by humans in space 5 times, allowing it to be one of the longest-running and most expensive science missions to date. For more than 30 years, through its powerful imaging system, it's changed our understanding of the universe. Galaxies, nebulae, and star clusters have been seen like never before.
The Hubble Space Telescope grew from the idea that by putting an observatory into space above the atmosphere, you could get much sharper pictures without that blurring that the Earth's atmosphere brings. So looking at places in our own Milky Way where stars are being born, and we're beginning to see evidence for planets being born in disks of gas and dust swirling around those stars, Things that weren't even thought of at the time when Hubble was built include measuring the atmospheres of planets going around other stars. And then beyond that, of course, the very big picture has been looking at galaxies all the way back close to the beginning of the universe.
Perhaps one of the most well-known images came from what's known as the Hubble Deep Field. Instead of looking at previously known galaxies observed from ground-based telescopes, they pointed Hubble at a relatively empty part of the sky and took hundreds of long exposures over a 10-day period, then combined them. This first image changed the way humanity saw the universe. Almost all of the roughly 3,000 objects captured here is a previously unknown galaxy.
So Hubble has actually helped us illustrate the evolution of the universe from the first cold gas and dust, which was lying around millions of years after the Big Bang, and how that coalesced and agglomerated and swirled together to form galaxies full of shining stars. So that's one of the great successes of Hubble. So to follow on from that science and see the birth of the first galaxies, we need a bigger telescope, and we need one that operates in the infrared, and that's the James Webb Space Telescope.
JWST is named after James E. Webb, NASA's second administrator who oversaw the agency's decade-long effort to reach the moon. He believed NASA had to put as much emphasis on pushing space science as human space flight. This next-generation telescope is not only 100 times more powerful than Hubble, but its ability to see infrared opens up a world of opportunities. It means that scientists are now able to detect frequencies of light that are invisible to Hubble.
The Hubble Space Telescope operates primarily in the optical, so the wavelengths that you and I can see. But as we look at the most distant galaxies in the universe, because the universe is expanding, those galaxies are, in essence, receding from us at faster and faster speeds. And that means that their light is shifted from the visible into the near infrared. So in fact, when we want to see the very most distant galaxies, the first ones which ever formed in the universe, Hubble can't see them. It's unable to see at the right wavelengths, and also it's not really big enough to see those extremely faint objects.
This shift in wavelengths is known as redshift, and the result is that the most distant objects emitting visible light are invisible to telescopes tuned to optical wavelengths.
So you need a big telescope operating in the infrared like JWST in order to see those very first galaxies, the ones which are moving so fast away from us that all of their light is redshifted into the infrared.
Now, JWST's largest program during its first cycle is going to put those capabilities to the test.
The Cosmos Webb survey is going to be looking 13.5 billion years into the past, about 200 to 300 million years after the Big Bang. And what it's going to be able to do is observe galaxies that are much further away from us than we've been able to do before. So we're going to be able to find some of the earliest galaxies that have formed in the universe. The Hubble Deep Field looked at one part of the sky and stared there for a long time, and that was really our first look into the distant universe. With Cosmos Webb, we are going to go a big step beyond that. So not only will we be able to look at objects that are much farther away from us and much deeper into the universe's history, we're going to cover a much larger area of the sky. So we're going to be able to observe many, many thousands more galaxies than were able to be seen in the small area of the Hubble Deep Field. So right now with Hubble, at these early universe time periods, you don't see very many, and what you see is kind of a smudge, just a little bit of a blob. With JWST, we'll be able to resolve structure, and we'll learn a lot about the properties of our very early universe, how the earliest structures first started to grow. But JWST will also tell us a lot about how those galaxies evolved from the very early universe until today, because we'll be able to see galaxies across a wide range of distances all the way back. So we can put together a timeline of how galaxies evolve and how their structures have grown overall. The images are going to have a very high resolution, which means we can resolve a lot of structures and see really fine details that we can't do with Hubble. So I fully expect some of the initial images we see are going to be jaw-dropping. And so overall, we estimate that we're going to detect several thousand galaxies in the very early universe, but how many we actually detect tells us something very important about the physics. So even if we detect less than we expect, that's still really interesting from a scientific point of view. If you had spoken to people that were expecting observations from the first Hubble data when Hubble first launched and told them about all the amazing discoveries Hubble has made since then, it would probably blow their mind, right? They never would have imagined we'd see galaxies as far away as we do, or that we'd observe, planets around other stars, etc. So we fully expect the James Webb Space Telescope will find things we never even knew to ask about.
Unlike JWST, we can't see infrared light with the human eye, but we can detect it through heat or experience it visually using an infrared camera.
Infrared light, you can sort of think of it like heat radiation. So everything glows in infrared. You and I are glowing in infrared.
A lot of things in space give off infrared light too, like stars, nebulae, and galaxies. But to detect the faint, faraway targets scientists are after, JWST has to be away from the Earth's warm atmosphere.
And the problem is with Hubble is that Hubble is actually quite warm. Hubble is in low Earth orbit and it's about the same temperature as the Earth. And that means it's actually emitting in the infrared. And that's a bad thing if you want to detect faint infrared light from very far away, because you're swamped by the light coming from the telescope itself. So the James Webb Space Telescope has to be cold, really cold, minus 233 degrees Celsius cold. So the way we achieve that is firstly by making the telescope open. It doesn't have a tube around it, but what it does have is a huge sun shield, and the telescope sits behind that sun shield. We're also located at a place called L2, 1.5 million kilometers away from the Earth, where the sun and the Earth are always on the same side of the telescope.
In this location, the telescope's main instruments can cool to near absolute zero temperatures and receive the infrared light. Then they can take that light and produce images, or analyze the light to learn what materials are present. This is known as spectroscopy and is a major feature of JWST's science instruments.
We have 4 instruments on the telescope, and these different instruments are optimized to do different things. So obviously the imagers take images of the universe in both the near-infrared and the mid-infrared part of the spectrum. The spectrographs take spectra of different objects in the universe. So spectra are sort of like, you can think of them as like fingerprints of the objects. So spectra help tell us about the chemical components and what atoms and molecules are in the various different things that we're looking at.
Using 2 of these instruments, NIRCam and NIRSPEC, and the power of the telescope, one team is going to be able to take images and reveal the composition of individual stars in our nearest large galaxy, the Andromeda Galaxy.
So we'll be looking 2.5 million years into the past. That means that the light that we're seeing was emitted by the galaxy 2.5 million years ago. Andromeda is the nearest large galaxy to the Milky Way. It's our sort of twin, if you like. They're both disk galaxies, and it's actually moving towards the Milky Way as well. They're kind of gravitationally pulling each other towards one another, and eventually will actually collide. We see the Milky Way from inside, and that means that we can just see the individual stars in the sky. When we look at galaxies outside the Milky Way, we just see them as a whole, and you can't really pick out individual stars. The great thing about Andromeda is we're still looking at it from the outside in, but we can actually pick out individual stars in the disk of Andromeda, which it makes it a fantastic tool for doing this kind of comparison where you want to extend the science that we're doing in the Milky Way to this whole kind of galactic population. Because we study the Milky Way in so much detail, it's kind of like the Rosetta Stone of galaxy formation that we can use to sort of inform our understanding of galaxies. But of course then if the Milky Way is an outlier and galaxies like Andromeda look much more kind of run-of-the-mill, then that means a lot of the things that we know about the Milky Way are not so useful. Other telescopes, while there's plenty of telescopes that are good, they're just not quite good enough to do this task. So we're going to take spectra of 300 stars in the disk of Andromeda. And so what that means is by measuring the regions of those spectra where we see less light, we can actually understand the element abundances, like oxygen, magnesium, and silicon. Before we take those spectra, we're going to use the NIRCam, which is the near-infrared camera. And we're going to essentially use that to take images of Andromeda before we go and take these spectra to make sure that we can really target the regions of the galaxy that we need to. What I'm interested in doing is sort of going and checking whether this characteristic element abundance distributions that we see in the Milky Way is present in Andromeda, which is something that we've not been able to do without JWST. We know that all the galaxies we see in the universe have kind of been forming throughout the whole history of our universe. So galaxies that we see are like a sort of fossil record of the whole of galaxy formation. If you could link all of the dots together and you understood galaxy formation very well, you could actually turn back the clock on all the physics that happen in those galaxies and get to something like the initial conditions of our universe, where all of everything came from. And I think those things are just kind of interesting. And a project like this is kind of telling us about the origins of our own galaxy. You know, most of us want to know where we came from.
Building a telescope that has enough power and sophistication to enable these sorts of projects wasn't straightforward. Engineers had to come up with a completely new design in comparison to Hubble.
So this telescope has this giant mirror, about 6.5 meters across, about 22 feet, and it has a sun shield that's the size of a tennis court. And so it's sort of an odd-looking design, an odd-looking telescope. The reason it was designed this way is because it's so big. It stands about 4 stories tall, so it's too big for any rocket to fit inside, all unfolded in a rocket. So we had to fold it up to fit inside the rocket, and it unfolded once it was in space.
Since spacebound rockets do fail from time to time, over 3 decades of work, $10 billion, and thousands of scientists' work were on the line.
And we have engine start. And liftoff. Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
Honestly, the launch was definitely not the hardest part of this mission. So following launch, we had 2 weeks of really intense, complex, complicated deployments to get this telescope unfolded. And myself and I think all of us on the team were really on the edge of our seats to wait for these deployments to happen.
Given its distance to Earth, if something went wrong with JWST's deployments, there wouldn't be repair missions like there was with Hubble.
The deployment of the sun shield was particularly intense. The sun shield itself is 5 layers, and it had to unfold and then deploy the 5 layers. And there were hundreds of release mechanisms on the sun shield that all had to release at just the right time and just the right way. There were quite a few single point failures, so that if one release mechanism didn't work, there would be nothing we could do to fix it. And so this particular part of the deployments, watching the sun shield deploy, was incredibly stressful, but everything went off so well. The engineers have built an amazing, incredible telescope. And after that 2 weeks, I think all of us took a deep breath. There was definitely a big celebration after the last part of the deployments happened.
The launch was so incredibly efficient. Using less fuel than anticipated, it extended the mission from 5 years to an estimated 10 to 15 years. Months later, after the instruments had cooled, there were a series of calibrations to make sure everything was aligned.
The primary mirror is made up of 18 different segments, and those segments had to be perfectly aligned once the telescope was in space. And so what we did was point the telescope at a bright star, and then you essentially get back an image of 18 different stars. And so from using that image and sort of tracing the star image to the different segments, we were able to individually move and tweak each segment to get the telescope to align on this star.
Each mirror had to be aligned to within the billionth of a meter to form a single primary mirror. That required making ultra-fine adjustments equal to 1/10,000th the width of a human hair, which took roughly 3 months to complete.
So once that was done, we got back this beautiful image of what's otherwise a boring star that proved that the telescope was aligned. For me, one of the most exciting things about this boring star image is the fact that in this relatively short exposure, you could see galaxies in the background. And so it gave us a little hint of what's to come with this telescope.
The star calibration image gave us the first glimpse of JWST's power. It will give scientists the ability to peer into star-forming regions and to witness their birth more clearly than ever before.
We'll be looking back in time between 20,000 and 200,000 years. We will be looking at 3 massive star-forming regions. One is in the Milky Way, our galaxy, and 2 are in nearby galaxies, the Magellanic Clouds. NGC 3603 is a massive star-forming region located at about 20,000 light years away from us in the Milky Way. And it is made up of many stars, many massive stars, some of which are even 100 times more massive than the Sun, but there are many, many smaller stars, stars like the Sun. The Tarantula Nebula is located in the Large Magellanic Cloud at a distance of about 150,000 light years. The Tarantula is a massive nursery of star formation. There are millions of stars there that were just born, and some of them are still being created, being formed. And the third region that we want to study is called NGC 346, is further away still, about 200,000 light years, in the Small Magellanic Cloud, yet another galaxy. In each one of these regions, we will select about 100 stars, and we will look at them very carefully by blocking everything else. We want to get only the light of those that we are interested, so we can disperse the light and produce a spectrum, very clean. But then, with the camera, we will look at the entire regions, and there will be easily millions of stars that we'll be seeing in these parts. We will be looking at the massive stars, but we are particularly interested in stars like the Sun, because those are the most likely ones to have planets around them. The main goal is to understand what is the difference in the way in which stars form in our own galaxy and also in nearby galaxies. But unfortunately, visible light doesn't travel well in regions where you have lots of dust and gas. And the regions where stars are forming are full of dust. So in those regions, it's very difficult for visible light to go through. But infrared light has longer wavelength, so the light rays are able to go around those particles, and we can see light even when there is lots of dust. So we can see through the dust. Stars are the building block of galaxies. They produce most of the power, the light in the universe. And they also make up the elements. Elements like carbon, oxygen, nitrogen, iron. Most of the elements in our body were actually made up in a star. And in fact, there is more. Some of the heavy elements in our body, like gold, copper, zinc, actually formed when a massive star exploded as supernova. So even though studying how stars form will not tell us who we are as human beings, it will definitely make us understand, make us realize that without stars, we would have never been there in the first place.
But it's not all about stars and galaxies. JWST was also built with a relatively new, exciting field in mind: exoplanets. Planets that are outside of our own solar system. Although there weren't any confirmed exoplanets while Hubble was being designed and built, it has contributed significantly to this emerging field, giving us this first visible light image of one. Now, there are over 5,000 confirmed exoplanets, and in the last few decades, we've learned that the overwhelming majority of stars have planets.
JWST has capability to study exoplanet atmospheres to a degree and precision that has never been done before. And so the infrared part of the spectrum offers a really great insight into some of the really interesting chemicals that might be in a planet's atmosphere. Things like water vapor and carbon dioxide and methane. Things that could possibly signal a surface that is habitable.
And there's one particular system that's on everyone's mind. It's called TRAPPIST-1, and it has multiple planets in the habitable zone, the orbital region around a star in which an Earth-like planet can have liquid water on its surface and possibly support life.
And that allows us to measure the radius of the planet, but also we can actually probe the atmosphere. So the light that is filtered by the stars, by measuring the colors of the atmospheres, give us a lot of information about the atmosphere. It's called transit spectroscopy, and that's a technique that's been used with Hubble, but with some limited performance, and the James Webb Space Telescope will be very well optimized to do these kinds of very delicate observations. The TRAPPIST-1 system is by far the best system. This is the one that will give us the strongest signal, and there will be lots of time devoted to that system with all science instruments on board the JWST. It is to do with the fact that the star is very close, so there's lots of light we can get from the telescope, and also the relative size of the planet to the star is relatively large, and that makes things much easier. We love small star and big planet, and for Earth-like planet, well, the TRAPPIST-1 system is just the perfect system. I think just knowing that these planets have an atmosphere and knowing that we have a planet in the habitable zone and there's water on it, That would be a big, big deal. That would be a first step into, look, this is here. We need to look in that system.
Dr. Doyon was among the scientists who worked on the telescope as principal investigator of the instrument provided by the Canadian Space Agency. The telescope was such a massive undertaking, with numerous science goals and technical challenges, that it required the collaboration of NASA, the Canadian Space Agency, and the European Space Agency.
So with the James Webb Space Telescope, which astronomers started thinking about as early as the end of the 80s, even before Hubble was launched, European astronomers were involved along with our American colleagues and with the Canadians from the beginning, from the outset, and build a bigger and better telescope than would be possible with just one agency alone.
Scientists who worked on the telescope were allotted time, but anyone could submit proposals from anywhere in the world.
This whole process is dual anonymous, so don't know who's proposing and who's doing the grading, and that's the way that the telescope time is allocated. One of the great things about these NASA astrophysics missions is that anyone in the world with a good idea can apply to use time on the telescope. And that happens. You know, we get proposals from around the world to use the telescope, and at the end of the day, the best proposals are chosen.
Anonymous proposals meant that bias was kept to a minimum and ensured that JWST covered a broad range of science goals, even ones focusing on our own solar system.
We are looking at the farthest regions of our solar system, so this is 4.6 hours that the light takes to come to the Earth. The acronym Transneptunian Objects, TNOs, these are objects that are orbiting beyond the orbit of Neptune, so in the coldest regions of our solar system. There are estimated to be billions of transneptunian objects, even if at this moment we have only discovered around 3,000 of them. TNOs are one of the most pristine bodies in our solar system. That means that they have been not too much processed since they formed. So they hold clues and they hold information from the very first stages of the formation of the solar system. This basically means that they are like frozen time capsules that are there waiting for us to unveil those secrets. The largest objects in the Transneptunian belt, together with Pluto, is Haumea, Iris, and Makemake. And because they are so large, they have activity, they may have an atmosphere, they have a lot of ices, like methane, nitrogen, CO. Those are in the largest TNOs, and we think they were an ingredient for the formation of all the TNOs. But when it comes to really know what is on the surface of these objects, we don't really know. So we want to look if in the smaller TNOs there are also some amounts of these ices. We want to know which are the ingredients that are on the surface and which is the state, the physical and chemical state of these ingredients, the recipe to cook a small body. We have 60 TNOs in our sample. We have representation of all the colors. What we are doing is we take the light that comes from one of these bodies and then is channeled through this instrument. Is called NIRSPEC, and this is a near-infrared spectrograph. NIRSPEC is going to observe in a part of the light that can't be reached for TNOs from the Earth. So we are just separating the light to get to know really each single material that can be there. So James Webb comes on time and is perfect to do this science because it's out of the atmosphere. We have a preconceived idea of what is a TNO based on the knowledge that we have, but our knowledge is limited. And the best things about tools like JWST is that they are really discovery tools. They are going to provide us with many answers to questions that we didn't even know we had.
Apart from JWST, many ground-based telescopes will be coming online in the next few years, complementing the science JWST will do. Like the Vera Rubin Observatory in Chile, estimated to come online in 2023. It is a wide survey telescope expecting to discover thousands of new objects like TNOs, so then telescopes like JWST can look at them in more detail. And the next big space telescope is just around the corner.
The big telescopes like Hubble and JWST only come along, once every couple of decades. And the next big telescope like this that we're building is the Nancy Grace Roman Space Telescope. So that particular telescope is not quite as big or expensive as JWST, but it is also an infrared telescope that's designed to see the universe in more of a broad sort of swath. So telescopes like Hubble and JWST are designed to see small parts of the universe very deeply. But by looking a little less deep but more wide, we can learn different things about the universe. People often ask, are these telescopes worth it? And we're spending a lot of money on these telescopes. JWST is $10 billion. Hubble, from its inception in the late 70s all the way to now, is about $16 billion. And so the question of is it worth it is an important one. These are funded by taxpayers. And of course, all of that money that's quote unquote sent into space is spent right here on Earth, of course, funding high-tech jobs. But in addition to that, I think if we look at the past 30 years of Hubble and what we foresee as a bright future with JWST, if you put that in the context of money spent per year, it turns out to be less than a cup of coffee, a cheap cup of coffee, per citizen per year.
Human beings are curious. We all want to know from where we come. Yes, we exist because stars exist. And so it's good for us to understand what are the elements and the processes that are actually needed for us as human beings to exist.
I know for myself, thinking over the past year, the past couple of years, with so much going on in the world and so much negativity, having the positivity of a mission like this to look forward to, and something that's working and successful and is a symbol of people all over the world working together to achieve something that is technologically amazing. For me, that's awe-inspiring and gives me hope for the future of humanity.
It's so easy to get wrapped up in things that are happening on planet Earth and not go and think about these beautiful things that we see. But then on the other hand, it's like, things like understanding how stars work can teach us about nuclear fusion, for example, the way that the elements are produced in the universe. I think it's just a fundamental question that human beings should want to know.
Historically, whenever a new facility is put together and you ask a question 5-10 years later, what was the main discovery that the telescope made? Nobody could predict it. I can talk to you about all the kind of stuff we think we're going to be doing, but you know what? We don't know. And that's the most exciting part of this.
Who has not wonder about looking at the sky? Who does not wonder about knowing that we are not alone? All of that knowledge that wonders us, it comes because someone asks himself, what is that is out there?